Okay, in this recording, we're going to talk about linear regression and how to fit a line to a bivariate data set. So let's go ahead and do a little review and look at a previous example as well. When there is a relationship between two numerical variables, x and y, you can use the information about one variable to learn about the value of the second variable. For example, you might want to predict y equals the product sales for a month when the amount spent on advertising is x equals $10,000. The letter y is used to represent the variable you would like to predict, and this is called the response variable or the dependent variable. But in algebra, it's called a dependent variable. In statistics, we're calling y the response variable, and the other variable, the independent variable, or x, is in statistics called the predictor variable. Okay, so x and y in the context of statistics, we're going to use response variable for y and a predictor variable for x. We already know that scatter plots frequently exhibit a linear pattern. When this is the case, the relationship can be summarized by finding a line that is as close as possible to all of the points from your sample or in the plot. Before seeing how this is done, let's review some elementary facts about lines and linear relationships. And this is going to be a real brief review because we did a more extended review earlier. So in statistics, the equation of our line is going to be y equals a plus bx, and a particular line is specified by choosing values of a and b. For example, one is y equals 10 plus 2x, and another is 10 minus 5x. If we choose some x values and calculate y equals a plus bx for each value, the points corresponding to the resulting xy pairs, as we know, will fall exactly on a straight line. Okay, so that was your brief review, but before we stop doing that, recall what the meaning, the geometric meaning of a and b in the equation is. B is called the slope here, so it's always the number in front of x. And it is the amount by which y increases when x increases by 1 unit. A is the y-intercept, also called just the intercept or vertical intercept of the line. And more importantly, the y-intercept, the value of A, is the height of the line above x equals 0. So it's the height of the line above x equals 0. So take a look down here. We've got a couple. You probably already read this, but just briefly take a look at this again. So we've got a couple of diagrams down here, and we've got two different lines being graphed right here. Let me zoom in. We can do that. So right over here, we've got the graph. That's the orange line. The graph of this linear equation, y equals 10 plus 2x. And what's happening over here? The slope is 2. And so y will increase by 2 units for each 1 unit increase in x. So that's illustrated here. If you want to get to, if we're at this point on the line and you want to get to another point in the line, one way to do it is just increase the value of x by 1. So that'll take you over here to this point. And then when you increase the value of y by 2, then you go up this and locate that next point on the graph, right? So the slope can be used to graph the equation. If I wanted to find another point, I increment x by 1 and y by 2 again, and then bam, I get another point on the line. Also notice from this line right here that, and remember, here's the origin. So this is the point 0, 0, 0, 0. Notice that the y-intercept is this point here, and also notice that its height, its vertical height above x equals 0, which is another way to call the x-axis, x equals 0, is 10. So that's not surprising that in the equation a is 10, or the y-intercept is 10, because of course that's what the distance, the vertical distance from the origin is. Okay, so yeah, that's slope and y-intercept. There's another picture of a line which has a negative slope. This line equation is given here. You can tell the slope is negative because you can use the definition of subtraction to just rewrite the equation as 100 plus a negative 5x, which would make negative 5 the slope. Okay, so the slope is negative, and we can see that in the line, the graph of the line rather. And right, how do we use the minus 5? Well, for any point on the line, this is true. I'm at this point on the line, and if I want to get to another point on the line, then I just change y by 5. So I'd go down 5 units, and then increase x by 1. And so that's the slope, right? Which is the amount by which y increases when x increases by 1 unit. You can play this game with any finding these triangles and finding another point just using this slope. And I'm sure that's something you're familiar with. And also notice that the y-intercept is up here at 100, okay? And that's the same as the height that x is, or that 100 is above the origin rather, okay? So, but besides that, I want to talk to you about how to interpret the slope, the meaning of the slope and the y-intercept for a model equation, or in this case, what we're going to call an equation of least squares, or the regression line equation. So I want you to recall this example from earlier that we played with in that previous video. Here it is. We've got a sampling of birds. And in that sampling of birds, we've got 9 observations here. Here's obviously the list of birds. And we've got X and Y data for the for all 9 birds. So we've got a paired data set here where the value of n is 9, since there's 9 observations. Okay, fine. And recall earlier that we measured the correlation for this data set. You can see the scatter plot. The correlation was about 97%. So that value of R, the correlation number, right, where does that fall along the R-axis? Well, gee whiz, it falls right here, Tim. Right there. And so that indicates the type of correlation is strong positive correlation, close to 1, which means it's almost a perfect fit. In other words, there's almost a perfect linear relationship between the 2 variables. And if you recall from earlier, the graph of the best fitting line, or the model equation that we used for this this data set, the 9 birds, right? For each of the 9 birds, we have a average weight and we have a wingspan, right? Okay, so the 9 points are there. The regression line equation here, or the best fitting line is there. And we were given the equation for that, the model equation for that regression line is this: y equals 18.4 plus 0.15x. Okay, so this is old news. And this line can be used to predict values of y. That's old news. Let's go over here. and talk about the interpretation of the slope and the y-intercept of your linear model, or in this case of your regression equation or least squared equation of best fit, or least squared equation. So yeah, interpreting the slope and y-intercept in a linear model. You've already seen how the slope and y-intercept of a line can be interpreted in the context of lines as mathematical objects, or we pointed to the geometry of it, okay, in those previous two pictures. Okay, so you must think a bit more carefully before you interpret the meaning of the slope and the y-intercept in the context of the linear model, or the context of the bivariate data set, the values of x and y, what they represent. Okay, so this is because it is generally not the case that there is a perfect linear relationship between the variables that define a bivariate data set, because this is usually a sample. Okay, so look back at the scatter plot for the bird data, and notice that the points in this scatter plot form a linear pattern, but they don't all fall exactly along a straight line. There they are. Okay, so this means that while the line y equals 18.4 plus 0.15x can provide a reasonable description of the relationship between, in this case, wingspan and weight, it is not true that wingspan increases by exactly 0.15 centimeters when weight increases by 1 gram. Okay, so here it is, a correct interpretation of the slope. Okay, right, we know the slope of the line is that, 0.15 centimeters per gram, actually, is what the slope represents, and a correct interpretation of that slope right there would be to say that the predicted wingspan, or the predicted x value, the predicted wingspan increases by the amount of the slope here, 0.15 centimeters, when weight increases by 1 gram. So we're going to find a best fitting line, and it's used to find a predicted wingspan. So if you want to correctly interpret the slope for the this equation here, this is the way to do it. So there is another thing you need to consider when a line is being used to model a relationship in bivariate data. And of course, depending on the variables that define the data set, it might not be reasonable to interpret the y-intercept in a linear model. So sometimes when you're interpreting, it's just like they said, when you're trying to interpret, and here we go. This would be the case if an x value of 0 doesn't make sense. So if you go back to our graph of our best fitting line, and it's right over here in the data, right? We have a y-intercept, and that point corresponds to x equals 0. And it doesn't make sense to interpret 18.4, this number, the y-intercept, centimeters, as the wingspan of a type of bird that has an average weight of 0 grams. In addition, it is not appropriate to interpret the y-intercept if x equals 0 is far outside the range of data values. If you go, and this is also the case for the bird data set, because if you go back and take a look at it, where is it? The range of the x values are between 6 and it looks like 460. Oh, whoops, that should be the max. So yeah, so x equals 0 is outside of the range of the x values. And so the y-intercept doesn't have a practical interpretation here. Okay, but sometimes the y-intercept does have a practical interpretation, and let's take a look at the those definitions in an example here. So there it is. In a linear model, the slope is interpreted as the change in the y value, or the predicted y value or the value of the dependent variable associated with an increase of 1 unit in the value of the independent variable. It can also be interpreted as the average change in the value of y, or the response variable, associated with an increase of 1 unit in the value of the predictor variable. And if it is reasonable to interpret the y-intercept, it can be interpreted as the predicted value of the dependent variable, or of the response variable, when the value of the predictor variable is 0. Okay, so take a look at one more example to try to help you with this. And it's right here. Suppose that a linear model is y equals 100,000 plus 100x, and suppose that can be used to model the relationship between price and size of houses in a particular community. Well, we know the slope is 100. And the units on that slope technically would be $100 per square feet, or it would be dollars per, just dollars over square feet. Okay, and we know the y-intercept is $100,000. Okay, and so how would you interpret the meaning of the slope in the y-intercept? Well, yeah, it's not too hard. Suppose that this model is based on data from a sample of 50 houses that ranged in size from 900 square feet to 3,000 square feet. In this case, the interpretation of the slope is the predicted y value, or the predicted price of a house. It increases by $100 when the size increases by 1 square foot, or so $100 for every square foot. And the interpretation of the y-intercept, well, it's not reasonable. There is no reasonable interpretation of the y-intercept in this context, because the x values in the data set range from 900 square feet to 3,000 square feet, and 0 square feet is outside of that range. And in addition, it doesn't make sense to think about predicting the price of a house that has a size of 0 square feet. Okay, so that's that. And let's talk about the principle of least squares and how we use the math to find what's called the best fitting line, or the regression line equation, or the least squares line that'll best fit the data. If you take a look over here at these two diagrams, okay, consider this data set, this scatter plot here. It shows a positive linear relationship, and it looks like it might be fairly strong. But which line would best fit this data and could be best used to predict predict y values for x values in the x range of the data? So two possible lines are shown right here, and it's easy to choose between these two lines. It looks like line 1 would obviously be a better fit. If you take a look at down here in the next figure, it's the same data set, and there's two different lines, line 1 and line 2. I mean, which one of those would be better? Or I guess another way of saying this is, which one of these 4 lines would provide the best fit? We don't want this to be, we don't want to all come up with the different set of answers. So we want to come up with the same answer. And so let's talk about how that's done. To measure how well a particular line fits a given data set, you use what's the vertical deviations. from the line. So there's a deviation or a distance that each point is away from the line. So there's a deviation for each point in the scatter plot. Let's take a look at an example of that, okay? On the next page, I'm going to show you, or you read this already, but we're going to take a look at a scatter plot along with the graph of the line y equals 10 plus 2x. And what we're trying to do is find the vertical deviations that each point are away from this best fitting line. And so here's that graph. Let's talk about that. So we need to first figure out all of what, if we're going to find the best fitting line or the least squared regression line, we need to first find the deviations, the distance that each one of these orange points, the vertical distance that each one of these orange points deviates away from this line. Okay, and so here's a point right here. And let's just call that point, so this point right here is called x1. Let's just call it x1 comma y1. Looks like it's about 15. I'm just estimating by eye here. I'm sorry, nope, the x coordinate is 5 rather. So it looks like it's about 5 comma 15. Okay, and there's another point up here. All right, fine, but let's take a look at this point. This point is deviating away from the line in the vertical, and that's just a vertical distance from the point to the line. So each one of these points in the sample has a distance, a vertical distance that it is away from the line. And that's what the deviation of each value is. So if I want to find the first deviation or the deviation of the first point, okay, then it's just going to be y1, so 15, minus the height of the line, at x equals 1. I'm sorry, at x1. And that's just equal to, let's see here, well, it'd be 15. Right, because the y coordinate of this point looks like it's about 15. Okay, and then now we're looking for the height of the line at x equals 5 or x1 equals 5. All right, so let's see, that would just be the height that this point is from the x-axis, and it looks like it might be about 19. This is about 19, and so the deviation of that first point is just going to be -4. The reason the deviation is negative is to indicate that the point is below the line. So we can find let's see, there's a 1, 2, 3, 4, 5, 6 points in the scatter plot or in the bivariate data set, and you can find a deviation for each one of those. And the deviation for, let's see, they've got some points labeled here. They're calling this point 4, and that's at 15. The coordinates of that point are 15 comma 44. And so if you want to find the deviation of that value, I'm sorry, of that point, well, then you're going to find what's called the fourth deviation. We could do this for the points 2 and 3. Okay. Actually, nope. Let's see here. The mistake I'm making is that if we make this point 1, point 2, point 3, point 4, point 5 right here. So if this point here is 0.5, then if we want to find the fifth deviation or the deviation of that point, then it's just going to be y5. minus the height of the line at x5. So that's just 44. The y value of the point from the scatter plot minus, and to get the height of the line at x5, okay, can we measure that? Okay, so what we would be looking for is, what is the height of this point above the x-axis? And it looks like its height would be 40. And the other way to get 40 for that height is to just use the linear equation, right, that models this, 10 plus 2x, right? And that's what they did here. They put 15, the x coordinate, in for x. Okay, this number here is 40. Okay, and then that makes this distance, this deviation length, vertical distance, 4. Okay, so I want you to notice a couple of things here. Notice that a deviation is positive for data points that fall above the line and negative for data points that fall below the line, right? When we found the deviation for this point right here below the line, it was negative. The deviation of this point, which is above the line, right, it was positive 4, okay? And a particular line is a good fit if the data points tend to be close to the line, right? If all the lines are packed in, if all the points are packed in close to the line. So this would mean that the deviations from the line would be small in magnitude or in absolute value. Looking back at figure 4.11b, so that's this figure, you can see that line 2 does not fit as well as line 1 because the deviations from line 2 tend to be larger than the deviations from line 1. And line 2 does not fit as well as line 1 because the deviations from line 2 tend to be larger than deviations for line 1. To assess the overall fit of a line, you need a way to combine your n deviations into a single measure of fit. And of course, the standard approach is to square the deviations to obtain non-negative numbers and then sum up those squared deviations. So that is what the meaning of this definition down here is. Okay, we've got a bivariate data set, and it's usually a sample data, and we've got the points x1, y1, we've got the points x2, y2, x3, y3, and so on, all the way up to xn and yn. So we've got n points or n observations in our sample. And let's take a look at this formula right here. Okay, it's called the sum of squared deviations about the line. This sum is just equal to this distance squared plus this distance squared, etc. But what is this distance right here? Well, we found out what that distance was for the first point of this data set because we happened to have the best fitting line. So at this point, we already found out what the deviation was. If you square this number, -4 times -4, you're going to get 16. And that's what this number is. So it'll be 16 plus, and then this is the next deviation, and then plus, and you've got to square that, and then plus the next deviation squared. So this formula, this left-hand side of this formula, is called the sum of the squared deviations. And you can use the sum of squared deviations to judge how well your line fits your data. For a given data set, you would like to find the line that makes this sum, that makes this number as small as possible. And that line, when you find that line, it's called the least squared regression line. or the line of best fit. The least squares regression line is the line that makes the sum of squared deviations, this number, the smallest. Okay, let's take a look at this example over here. Okay, so take a look here. I've got a scatter plot, a different scatter plot, and it looks like there's points A, B, C, D, and E, the blue points. Those are the data points, or the points in the scatter plot. And I put a line in here. It's just this red line. And this line, it was just a guess at what the best fitting line might be for this data set. And if I want to assess the fit of this line that I put in, then I need to find the sum of squares, which is going to be this number. Okay, so take a look at this. Let's go back over here. See if I can. All right, so I'm trying to illustrate how we find the best fitting line. And we know, of course, yeah, we've got to use this formula to find the sum of squares to assess our guess at what the best fitting line is here, the red line. And that sum of squares, it's easy to find. If you take a look, each one of these points, the point A, it deviates away from this, our guess at what the best fitting line is. And it deviates away from there by, it looks like, about a distance of 2. And since this point is above the graph of what we think is the best fitting line, the deviation here will be a positive 2, roughly. And if we square that deviation, if we square 2, we get 4. So you see, we're making a square out of the point, and that's with the area of that square represents the deviation, like this number squared. The next point B, it's also above the x-axis, and it's about 2 units. If you can, here's the x-axis, you can tell it's about 2 units above what we think is the best fitting line. And so the deviation length is 2, and the deviation length squared would be about 4. Okay, so point C, it's up here, it's below the line. And so this deviation length here, the vertical deviation, is -1. And that deviation length squared is -1 times -1, or just 1. Okay, so all 5 of these points have a vertical deviation. And when you square those vertical deviations, you get a squared deviation, okay? And when you sum up all of these squares, all of these areas of all these squares, we're getting, let's see here, 4 plus 1 is 5, plus another 4, so we're up to 9. 9 plus 16 is 25, then plus 1. So we're up to 26.13. And is this the best fitting line? Well, if it was, then this number, or this number that comes out of this expression here, or the left side or the right side of this equation, whichever version you want to use, has to be the smallest. So what I can do here is I can move move the line around, okay, and try to find a better fitting line. And you can see, look at that, my sum of squares. Are you watching up here? My sum of squares, when I try to make a different guess as to what the best fitting line is, notice my sum of squares is decreasing, right? We were up here roughly, and now I'm moving the line. Well, this seems like it might be a better fit because the sum of squares is less than 25. And if you want to take a look at the actual least squares regression line graph, there it is. It's that green line graph. And if you try to take a look at what the sum of squares value would be for points along the green graph, one way to do that is to just take our guess and move our guess at the line onto the regression line. And you can make these calculations, the sum of squares calculation again, and you can see, look, it's way down to 16. And this is the smallest it will be for this data set. And so then going back to how we find the regression line is we take, what we did was we used a little bit of calculus and algebra to show that we can find the values of A and B if they're unknown with these that the values of A and B will be, that this will be at a minimum when A and B are from these two formulas right here. You can get the slope from this nasty looking thing and the y-intercept A from that. And of course, we don't want to have to do the problem that way. So I recommend just use the calculator, Lin-Reg t-test, to find the equation of your regression line. Okay, so going back to the bird example, the wingspan, where is that sucker at? I'm about to finish this up. Okay, I have this data set over here in my list 1 and list 2 already. Okay, and if I want to find the equation of best fit or the least squared regression line equation, remember, I'm going to press the stat button, arrow over to the test drop down menu, and I'm going to scroll down with my arrow key until I find the Lin-Reg t-test command. And then I'm going to hit enter. I get this settings window. I need to tell the calculator where my data is at. It's in list 1, list 2. Frequency is always going to be 1 for this type of calculation. These numbers, beta and p, we'll talk about that later, but just set that to not equal to 0. And the reg equation, if you don't have y1 stored in there, you don't have to have it in there. If you want to get y1 right there, then you just press the vars button, 5 for statistics variables, and whoops, no, that wasn't, let's go back here, vars, and then arrow over to y vars, and then hit enter, and then hit enter again. So anyways, when I calculate, I get the regression line equation, and this, the calculator will store the equation as y1, and then when I press the graph button, it'll graph the scatter plot along with the regression line equation. So we know the equation is a plus bx, and the value of a here is 18, and the value of b is about negative 0.16. So that was the best fitting line, about 18.4, right? The y-intercept plus about 0.15, 0.16x. So even though, and I didn't show you the calculus and the algebra about how we got these two numbers, A and B, and it's just from these formulas, but I didn't show you how we got those. To get these values of A and B, just use the calculator. But once again, the least squared regression line, right? It's a line, it's the only line that makes this number the smallest. So you can find this number for any line, but this number will be the smallest for only the line that best fits the data, or that's closest to all of the data points. Okay, and that's what the calculator does for you. It finds that regression line. So one last thing before we end here is, once you find your regression line equation, if there's a significant strong correlation between x and y, it's commonly, we did this earlier, it's common to use your equation to predict an x value, okay? And we need to caution you that you need to think twice about using your best fitting line to predict a y value for an x value that is outside the range of x values in the data set. And that's because you don't know whether the observed linear pattern continues beyond the range of the x data. Making predictions outside the range of the x data in the data set can produce misleading predictions if the pattern does not continue. This is sometimes referred to as extrapolating. So if you go back to that bird data, where's that? So there it is. And going back to that, notice that the minimum and maximum x values from the sample were 6 grams and 460 grams. And so we're not gonna use our regression line equation to make a prediction for any y value or get any y value for a value of x that's outside of this range. So we're not going to use our regression line equation for values of x that are less than the minimum here, and we're not going to use them we're not going to use it for values of x larger than the maximum, because if we do, that's called extrapolation. So the regression line can only be used to interpolate or find predictions for predictive y values for x inside the range of the x data.